I am Blanka Říhová. I am president of Czech Land Society, and I am just very pleased, we are very honored on behalf of the Czech Land Society to welcome here Professor Thorne. He's a famous and very much known scientist, and it's a great honor for Prague to have you here. So we are looking forward to your lecture. We are really honored and pleased to have you with us. Thank you very much. And now Professor Bichak will just modern or...
Yeah, I will speak just 20 minutes, not more. It's a great pleasure for me and a really honor for us to have Kip here. I must say personally I'm extremely happy because Kip helped to Czech physics and to me in particular just after Russian invasion. But I don't want to speak about these details. Kip, when he was celebrating his 60th birthday, there were about 200 people at the conference. So it was a big festivity. I was not, but I read an article about it. And the writer wrote about Kip, it's about shaman of space and time. But I would like first to speak about the priest to you, and not about shaman. And the priest is Bolzano. Why did we decide that there will be Bolzano lectures? Bolzano was a big figure. I was surprised, and I'm sure Kip would not know about this, that there is a historian of science, Norse, who wrote, you know, the book, but probably you didn't notice Bolzano. Mathematicians invited me when there was 200 years of Bolzano to give a lecture about black holes, actually. So, but I looked at this book, and I found that Norse says here, Bolzano was a Czech theologian and amateur mathematician whose modest mathematical fame was posthumous. His political beliefs were no less radical than his mathematics, and for the former he was removed from his position in the church. So Bolzano was, however, a really big figure. He wrote everything in German. However, he never left really Prague, or I would say Bohemia. So he supported many Czech people, and he was extremely noble character. He came to theology primarily because he wanted to do something by which he could serve to other people. And then his sermons were too liberal and too open-minded, and so that he started to do mathematics. Now, he's quite well known today by mathematics, so you know probably, or our students here, Bolzano-Cauchy criterion for convergence of sequence. There is Bolzano-Weierstrass theorems, etc. And so this is all known, but I think Bolzano would deserve to have somebody to summarize his attitudes to physics, because Gemmer, this forward of Einstein, and the same with Norse, who devotes him 3 pages. So they speak how he distinguished between bounded spaces and spaces unbounded but still finite, like, for example, surface of the sphere, but the wedge, for example, is bounded, etc. So I will not bother you with this more, but he was certainly a very ingenious figure. The only thing which I want to say about Bolzano is that you should take him seriously when you are sick. This is a beautiful booklet, which I'm very surprised that appeared during communist time. It's his own autobiography. And he speaks about how he was quite often sick, how when he got very sick, so he took Euclides' elements. And Euclides' elements made him really healthy. The sharp-mindedness of this, it would be nice to read it in Czech, but this would be too long. So Bolzano deserves, I think, our attention, and that is why we organized the second Bolzano lecture, and because actually a cosmologist is concerned with Bolzano, so I think it's very appropriate to have here Kip. Now, it's horrible to ask you, but would you please project me first? Yeah. So you see, Kip comes from Utah. And in Utah, people are very much touched with genealogy. So this is his grandfather. It's not so only that you would smile. The reason is that actually, as you probably most of you know, Einstein spent, of course, most of his end of life in Princeton. And there was John Wheeler, who was supervisor of Kip Thorne, as well as of Richard Feynman. And it was John Wheeler who really started big renaissance of general relativity in the United States. And so in this sense, Kip is really, in scientific sense, grandson of Einstein. this is moreover on the soil of Caltech. And it is, Einstein was visiting briefly only Caltech. And the next, please. So this is Kip, as I experienced him in '71, always admired by a big group of people. He had about 50 PhD students altogether, but some of them became very well known, Cliff Will, Bill Press, and others and others. And this actually is not my picture, but it's from the same time when he had a lecture, I think When the Sun Dies, and this was for children here. So let me not take too much time, because you are not looking forward to me but to him, but let me say the last word that which Richard Isaacson used. Richard Isaacson was quite important figure, who did quite important work in his PhD thesis about gravitational waves with high frequency, about energy momentum tensor, which is included in the big book about which Kip, I think, will speak. Sorry, I will quote Isaacson in 20 seconds. I have to say that I found in my notes from Caltech, Kip today wrote a 60-page paper during one day. And this is incredible with him, and actually he, I think, mostly contributed to this big Bible, which, well, I would be talking too much. Which became the basis for general relativist teaching and learning in all over the world. But to my big surprise, I found that he produced, together with Blandford, one of the great astrophysicists, English by origin, a student of Martin Rees. So they produced a big book, which somebody already here brought, which is called Modern Classical Physics. And this was published 2 years ago in Princeton University Press. So I don't know, and it looks that Kip is sleeping normally. But when you do all this work, it's really admirable. So, but let me finish with this quotation from Richard Isaacson, because he was the man who ruled the money in National Science Foundation for gravitational wave detectors. And he, in one meeting, said that actually I feel that Kip Thorne is our national treasure. And I think this is a mistake, because he is international, he is worldwide treasure, but today we treasured him here in Kingdom of Bohemia. So please, Kip.
So thank you very much, Yishi. Is the volume right for you? It's okay? Okay. It's a great honor for me to be here to give the Bolzano lecture, and here at the Charles University, a great center at which so much very important physics and other science has been done over the centuries. But I'm going to begin actually 1.3 billion years ago, when here on Earth, multicell life was just forming and spreading around the globe, but in a galaxy far, far away. A quotation from my dear friend Carl Sagan. 1.3 billion years ago, there were two black holes that were orbiting around each other. Here you see the shadows of the black holes. If you can see it, this is a little bit dim, against a field of stars behind. The light from the stars is bent, like the bending of the light around the sun, but the light can come in and go around the black holes several times and come to your eyes. And as a result, as the two black holes go around each other, you see marvelous swirling patterns caused by that gravitational lensing. The two black holes circled around each other, emitting, as they went around, ripples in the shape of space and time called gravitational waves. And as these waves carried off energy, the black holes then spiraled together. Having lost energy, they crashed together in a great, gigantic collision that I will talk about in more detail a little bit later. And the waves then from that collision, as a burst of gravitational waves, went traveling out of the galaxy in which the black holes lived into the great reaches of intergalactic space. They traveled across intergalactic space for 1.3 billion years. until 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. This burst of gravitational waves reached the outer edges of the Milky Way galaxy. They traveled through the Milky Way galaxy for 50,000 years, and on September 14 of 2015, they arrived at Earth. They arrived first at the Antarctic Peninsula. They traveled up through the Earth, unaffected by all the matter in the Earth, and emerged at the LIGO Laser Interferometer Gravitational Wave Observatory in Livingston, Louisiana, in the southeast of the United States. 10 milliseconds later, they emerged from the Earth at the LIGO detector or observatory in Hanford, Washington. As they passed through these detectors, they stretched and squeezed space, correspondingly stretched and squeezed these arms, which I will talk about in a few minutes, stretching along this arm, squeezing along that, stretching along this, squeezing along that. And these instruments were designed to measure this stretching and squeezing of the gravitational waves. And then the data from that went into a computer and were analyzed by a team of 1,000 people. These detectors were built by a LIGO team, but there's a second team called Virgo, which did not yet have their own detectors operating. They joined together with our LIGO team in analyzing these LIGO data. These are just a few of the 1,000 scientists and engineers who were involved in this. And this team struggled for 5 months to be absolutely sure that this signal was really due to gravitational waves. I'll explain why it was such a struggle in a few minutes. And then when we were completely convinced, we announced the result to the world. And when we announced the result, it was front page headlines in all the major newspapers around the world. It was one of the biggest discoveries in science in the last few decades. So I'd like to describe how we got here. How was this gravitational wave detector built, these detectors built? How were we then, with the aid of this, creating what we now call gravitational wave astronomy or gravitational astronomy? The story begins with Albert Einstein in 1916. Einstein, having formulated his general relativity theory with the seeds, the first major steps in that formulation done here in Prague in 1910 and 11. Einstein then predicted in 1916, 100 years before our announcement, he predicted the existence of gravitational waves. And as he described them, these gravitational waves stretch and squeeze space. And you can think of this by laying down a rectangular grid of particles out in interplanetary space, far from all gravitating bodies. And as the gravitational waves go by, propagating into the screen, they push these particles together along that direction, apart along this direction, and then that squeeze and that stretch along these two directions oscillates in just the pattern that I'm showing to you. So that's the physical manifestation of the gravitational wave. And so the challenge then was to detect these gravitational waves, and Einstein in 1916 looked at the numbers for his predictions for the strengths of these waves and said, humans will probably never see these waves because they are so very, very weak. And yet, in the 1960s, Joseph Weber at the University of Maryland began the first construction of a gravitational wave detector aiming to go after these waves. What had happened in those 50 years since Einstein's prediction? What had happened is that there were new sources of gravitational waves that Einstein had not known about, black holes and neutron stars, about which I will speak, which were far stronger sources of gravitational waves than anything Einstein imagined in 1916. In addition, there was new technology, lasers, computers, and ever so much more that enabled you to build detectors far more sensitive than Einstein dreamed of in 1916. In 1966, having been very much influenced by Joseph Weber and also by John Wheeler, my PhD advisor at Princeton, I moved to Caltech as a professor on the faculty, and I started a theory group, a group working in theoretical physics with a major focus on black holes, neutron stars, and gravitational waves. And together with my students and colleagues elsewhere, I began to develop a vision for what science you could do with gravitational waves if they could be detected. A vision for what we called gravitational wave astronomy. And this is from my first paper about that vision in 1972, written together with my student, William Press. And our vision was based in part on the enormous differences between the electromagnetic waves with which astronomers normally study the universe and gravitational waves. Electromagnetic waves are oscillations of the electromagnetic field that propagate through space as time passes. Gravitational waves are oscillations of the fabric, the shape of space with passing time. Electromagnetic waves in astronomy are almost always incoherent superpositions of the emission from individual particles, atoms, and molecules, whereas gravitational waves are emitted coherently by the bulk motion of huge amounts of mass and energy, for example, the orbital motion of these black holes. Electromagnetic waves are all too easily absorbed and scattered by matter, principally dust, as they travel through the universe. Gravitational waves are never significantly absorbed or scattered by matter, even if they're created in the earliest moments of the universe and propagate out from the Big Bang in those earliest moments. The implications of this are clear. First, many gravitational wave sources won't be seen electromagnetically because the two kinds of radiation are so very different, and because it's so hard to see through the dust with electromagnetic waves. So great surprises are likely, again because of the huge differences in the two types of radiation. We'll be looking at things that we had not imagined seeing before. And as a result, there is a great potential to revolutionize our understanding of the universe. Electromagnetic waves are you usually observe the time-evolving spectrum, that is the amount of energy at a particular frequency, measured over frequencies, or you see the spectra with the spectral lines, and you observe how the spectra evolve with time. Gravitational waves, we observe the waveforms. It would be like observing the electric field oscillating in time. We observe these waveforms that stretch and squeeze, and we watch this happen as time passes. Electromagnetic waves, most detectors are very large compared to their wavelength. Electromagnetic waves, most detectors, such as an astronomical telescope, are very large compared to the wavelength of the light. And that enables you then to get very good angular resolution on the sky, but also confines you usually to a narrow field of view. Whereas gravitational waves, most detectors are small compared to the wavelength of the gravitational waves, and so you see the entire sky at once, and you have poor angular resolution, and we expect that to continue until the 2050s, when there will be a new detector probably operating that is as big as the solar system, reaching across the Earth's orbit, and that should have high resolution. Electromagnetically, most sources are very large compared to the wavelength. The sources are large compared to the wavelength, and that means you can look at this piece of the source, that piece of the source, that piece of the source, and make pictures. Gravitational waves, the sources are not large compared to the wavelength, at least usually not, so we can't make pictures. Instead, we learn about the source from the two waveforms oscillating away, very much like we learn about the source of music from an orchestra with our ears. We're listening to gravitational waves from the instruments in the orchestra, and those waves then do not have good spatial resolution. You have trouble determining where the instruments are, but you get a lot of information from the oscillations of the waves as they and the emission from the various kinds of instruments. So if you can measure the waveform then, you could get a lot of information. So here I have a large black hole with a small black hole orbiting around it. As the large black hole spins, it drags space into motion around itself, and as a result, the orbit precesses. Each time the black hole goes around, the small black hole goes around the big black hole, there's an oscillation, a period of oscillation. As the orbit precesses, the strengths of the waves go up and down, oscillating. So you see there's a lot of information in this waveform of stretch and squeeze as a function of time. So that's how you're going to get the information. So we already knew all this in 1972. At the time that I was developing these ideas with Bill Press, I was also writing this textbook, nearly completing this textbook with John Wheeler. And Ray Weiss, whom I had known at Princeton when I was a graduate student there, and he was a postdoc, he had gone to MIT as a young professor, and he invented and wrote a paper about it, a technical paper, a new kind of gravitational wave detector. He said, let's take 4 mirrors and hang them from overhead supports. And we are looking down on those mirrors. And so the mirrors are swinging like that. That direction is down. And as the gravitational wave goes by, it pushes these mirrors together, pushes those mirrors apart, and then that oscillates. Let's send a laser beam in through a beam splitter, he said, and through a hole in this mirror and bounce it back and forth many times, and then return it through the beam splitter. And similarly, and bounce it back and forth many times between those mirrors and return, and then recombine the light of the beam splitter. If that happens, then as this separation decreases and that separation increases, the intensity of the light going toward a photodetector down here will increase and decrease. So you have an intensity that goes up and down and up and down, and so that's your gravitational wave signal. That shows you the gravitational waveform. This was a wonderful idea because the interference of the light between these two arms, as we call them, would give very high resolution. So you could really detect very, very weak waves, he argued. And so he called this a gravitational wave interferometer. I looked at this, and I did a few numbers for myself, and I thought to myself, Ray has gone crazy. There's no way this is going to work. And so I was in the final stages of completing this textbook with my PhD advisor, John Wheeler, and Charles Misner, another student of John's. And so I wrote very quickly, just before the book went to press, this is not very promising. I described it in a few sentences and wrote, this is not very promising. Now, why did I think it was not very promising? Let me give you some numbers. You have these mirrors that are being pushed back and forth by some amount delta L. They have a separation L. And these gravitational waves strain. They're fractional change in the separation, delta L divided by L. For the sources that I was thinking about at the time, I was estimating the strength of the waves would be 10 to the minus 21. That's a very, very small number. And that's 1 billionth of a trillionth. So it's a very small number. And if we imagine then a separation between the mirrors of a few kilometers, and we wound up with 4 kilometers for LIGO, then the motion would be 10 to the minus 17 meters. Now let me show you how small 10 to the minus 17 meters is for those of you who don't know, and even for those who do know. It's good for the soul to refresh your memory. You begin with 1 centimeter, divide by 100, you get the thickness of a human hair. Divide by 100, you get the wavelength of the light that is being used to monitor the motion of the mirrors. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of the atom. Divide by 100, you get the magnitude of the mirror motions. Mirror motions are just a little bit bigger than 1 trillionth of the wavelength of light, and you're going to use light to measure this? Ray was crazy, I thought. There's no way this could be done. Then, for, I guess, 2 years, from 1973 to 1975, I had long conversations with Ray about this, and with Vladimir Brzezinski. Brzezinski was a Russian physicist, a dear colleague and friend of mine, superb experimental physicist, also working in this field. And I studied Ray's technical paper, and I then became convinced that this really had a possibility to succeed. And because I had a vision for what we could do with these gravitational waves, I decided that I and my students would devote as much effort as we could, as much effort as was needed to help the experimenters pull this off, to help them succeed in detecting these gravitational waves. It was worth a lifetime effort, it seemed to me. And this did become a lifetime effort for me and for Ray Weiss, beginning back from when he and I both started thinking about these gravitational waves until the detection was approximately 50 years. And so let me give you a little bit of an idea of how I became convinced that this might be possible. So first of all, why did I decide you really could make a measurement that is that tiny using light? So the idea would be you bounce the light back and forth, say, 100 times. And so you begin with a gravitational wave signal that would be moving the mirror by 10 to the minus 17 meters. But each time you go back and forth, you build up the signal as you go back and forth, because these mirrors have been pushed apart by a factor of 100. And so the actual signal we needed to measure was 10 to the minus 15 meters. Okay? Now there's something called photon shot noise, which is the randomness in the arrival of the photons, of which the laser light is made up, at the photodetector at the output. And there's a theorem that says, as happens so frequently, that this randomness of arrival gives you then a noise that's at the level of this 1 over the square root of the number of photons. So in fact, using this technique, if you're clever enough and do it well enough, you can measure motions that are the wavelength of light divided by 2 pi, and then 1 over the square root of the number of photons you use. And using, say, a 10-watt laser, in a half of a gravitational wave period, you get 10 to the 18 photons. Square root of that is 10 to the 9. And so you begin with 10 to the minus 7 meters, which is the wavelength of the light divided by 2 pi, and a factor of 10 to the minus 9. The noise is at 10 to the minus 16 meters, and the signal is 10 to the minus 15 meters. So it wasn't crazy after all, just very, very hard, but not impossible. So that was one key issue. So then there's another issue that people really worried about. That is, surely if the gravitational wave stretches and squeezes space, then it will also stretch and squeeze the wavelength of the light. And so with the wavelength of the light expanding, as the mirrors move apart and contracting when the mirrors move together, you shouldn't be able to get any signal. Well, there was an answer to that. You use fresh light each half of a gravity wave period or less. So you're using one set of light when these mirrors are apart, and another set of light when they are together. Because it's true that the wavelength will stretch and squeeze as the gravitational wave goes by. But you just put the light in, store it for half a gravity wave period, send it back out, and continually using fresh light. And so that turns out to be a beautiful and simple solution to the problem. There's thermal noise. The RMS, the mean thermal motions of the atoms in the mirror's surface, have an amplitude of about 10 to the minus 11 meters, which is 100 million times bigger than the motion of the mirrors. And so, and these oscillations, however, are at frequencies of 10 to the 13 hertz. So they're much faster than the gravity waves we're looking for. We're looking for gravity waves with periods of about 1/100th of a second. So the key thing in order to deal with these motions of the mirrors, of the atoms inside the mirror, here's the mirror, the light beam's bouncing off of it. The motion of the atoms are, as I say, 100 million times bigger than the gravity wave signal that's moving the mirror. However, the light beam is averaging over, first of all, averaging over about a billion surface atoms in the surface of the mirror. It's averaging over about 100 billion atomic vibrations during a gravitational wave period. And with all that averaging, the result is that if you're really clever and you do it really well, the light is sensitive almost only to the motion of the center of mass, the average location of all of the atoms inside the mirror, through this averaging. That means that the mirror, so far as the gravitational wave detector is concerned, behaves like a 40-kilogram particle, a single particle weighing 40 kilograms. And that's all the light sees after all this averaging. There's a little bit of residual thermal motion that remains, and we call this thermal noise. And it's a huge problem to get rid of that final residual thermal noise, and that's a big source of the high cost of this, is the techniques that are used to deal with that. You also have seismic noise. The mean motion of the ground at the gravity wave frequencies we're looking at, say 100 hertz, is about 10 to the minus 10 meters, so that's about 1 billion times bigger than the motion of the mirrors caused by the gravitational wave. And so you have to have seismic isolation that prevents the mirrors from moving any more than 1 billion times less than the motion of the ground under the mirrors. So this is done with a complicated seismic isolation system, what we call active and passive seismic isolation. And so you have stacks of materials here to provide the seismic isolation. Then I've just drawn it in here. You have the mirror hanging from an overhead support, and you finally have this pendulum here. The mirror swings, and that provides additional isolation. But this isolation is very similar to what you have in a high-priced automobile. If you have a Mercedes automobile, you can go over a bumpy road and you don't feel bumps very much. And it's the same kind of principle operating here. So we understood these things, and we could see that it was possible to deal with all of the major noise sources that we knew about. And so we decided that we would actually create a gravitational wave experimental group at Caltech to go along with my theoretical work and work in parallel with Ray Weiss's group at MIT. We brought to Caltech a guy named Ronald Drever from the Glasgow University in Scotland. And we brought him because he had invented an improvement, well, several improvements on Ray Weiss's ideas. One of them is that he said, let's make each of our mirrors have the light bounce back and forth, making just one spot on the mirror. It comes in, it gets trapped, it goes back and forth, but you're not making many discrete spots. Basically, the idea is you coat the mirror with a coating, sort of like a silver coating on an ordinary mirror, but this is what's called a dielectric coating here, a dielectric coating there. You send the light in, the light leaks through the coating, it gets trapped in here and bounces back and forth 100 times or more, and then it leaks back out, and similarly there. But that meant you could have smaller mirrors because the light, being trapped in this way, is only making one spot on the mirrors, not 100 spots. So you could have much smaller mirrors, and this became much more versatile, it turned out. This, in technical language, you operate each arm as a so-called Fabry-Perot cavity. So from 1980 to 1983 at Caltech, led by Ron Drever and Stan Whitcomb, who we brought on as an assistant professor, who went on to become the chief scientist for the LIGO project, Stan and Ron and the team built a 40-meter prototype, a prototype that had arm separations between the mirrors of 40 meters rather than 4 kilometers. And at MIT, in parallel, Ray Weiss and his group completed work on a much smaller prototype, but more importantly, they carried out a feasibility study for these detectors that would have sizes of many kilometers, 4 kilometers in the end we chose. What were all the things that could go wrong, all the practical problems that you would have to face, and how would you deal with them, and how much would the whole thing cost? In 1984, with successful work on prototypes then at Caltech, at MIT, in Glasgow, and in Garching, Germany, and based on this feasibility study at MIT, we at Caltech, together with Ray Weiss and his group at MIT, created the LIGO project, 1984. From 84 to 87, the LIGO project was led by a troika of Ray Weiss, Ron Drever, and me. And we did continuing research and development for these detectors. We developed a preliminary design for the big detectors. We searched for and identified possible sites where we would build these. And we were the most dysfunctional, worst leaders of any large project that has ever been seen in the history of physics, as far as I'm aware. We could not get agreement between the two experimental groups at Caltech and MIT. There was a lot of fighting. Caltech was pushing in one direction, MIT was pushing in another direction. And it was obvious that this thing was going to fail with this leadership. And so withdrawing pressure from the National Science Foundation, Richard Isaacson, whom Professor Bichak mentioned in his introduction, who really was a fourth leader of this. He really was the person working from Washington who worked with us to enable us to make this happen in the end. With great pressure from him, we decided we had to bring on a single director. We brought on board a man named Robbie Vogt. And Robbie was at Caltech, and he catalyzed the Caltech and MIT team to work together. He did it by brute force, basically. He said, if you don't do this, the whole thing's going to fall apart. You have no choice. And the team listened and began to work as a real team. He expanded the project by doubling the size. He hired 25 new engineers and physicists because we knew we needed a larger group. And he led us in developing a conceptual design and then an engineering design. These are technical terms for certain levels of design work, on the basis of which, for example, you could get much more accurate costs for the project. 1989, under his leadership, we submitted a construction proposal to the National Science Foundation to build LIGO. We said we would first build the facilities, the big vacuum pipes inside which the laser light would go bouncing back and forth, and all the other things that were needed in addition to the detectors. And then we would build 2 generations of detectors, an initial detector, or interferometers as we called them, gravitational wave interferometers. A first generation that we knew how to build, but that would not have good enough sensitivity to see gravitational waves unless we were really lucky, unless nature was much more kind than we expected nature to be. And after that based on that initial generation of interferometers, we would learn enough to be able to build the second generation, the advanced interferometers. And those advanced interferometers would have a sensitivity at a level where we should see a lot of gravitational waves. It took us 3 years to get this project approved. Our big problem was getting through Congress. We were attacked by powerful people in the astronomical community who thought this money could be better spent with building conventional telescopes. They could not understand how you could build a first generation of instruments and not see anything. It would have to build a second generation. That's not part of the culture of astronomy. It's very much part of the culture of physics. And we were all physicists planning to do astronomy. So we had a battle, a political battle in Washington. But in 1992, after Congress approved the funding for this, from then until the ultimate detection in 2015, I have to count on my fingers, 92, 2002, 25 years, basically, nearly 25 years. Congress and the National Science Foundation backed us, supported us fully. They never cut our budgets very significantly through 2 generations of detectors. First generation saw nothing, as we had predicted. The fact that we were totally honest with Congress about what we had to do from the outset was key to getting this carried through with the funding over those about 25 years. So we began construction in 1994, and we brought on a new director, Barish, just before that. Barry had far more experience in running large projects than anyone else around. He was widely regarded as the most skilled physicist in leading large projects in the United States, perhaps in the world. So he led us through the construction of the facilities. In 1997, as the facilities were still under construction, he expanded LIGO. It was obvious to him that Caltech and MIT together could not begin to build a large enough group to pull this off successfully, because these instruments would be so complex. You needed a much larger team to build the various components and make them all work together. So he created the LIGO Scientific Collaboration, or LSC, which is now 1,200 scientists and engineers in 80 institutions in 18 nations. I think it's now 100 institutions. It continues to expand. And it was really this huge team that was essential to success and that really pulled this off for us successfully. As a measure of the complexity of these instruments and why it really took such a large team, from each instrument, from each interferometer, there are 100,000 data channels coming out. One of them carries a gravitational wave signal, and all of the rest carry information about what's happening inside the interferometers or in the environment around, information about what could go wrong. And that is a measure then of the complexity and tells you why it really took such a large team to pull this off. This is the complexity required in order to make measurements that are 1 trillion times smaller than the wavelength of light, a billion times smaller than motions of the ground underneath the instruments, and so forth and so on. To really pull that off required this complexity. So Barry led us through the construction of the initial interferometers and the first gravitational wave searches, and then he was stolen away by the high-energy physics community to lead the design work for the next generation of particle accelerators in the field of high-energy physics. And we brought on a third director, Jay Marks, and then a fourth director, David Wrightsey, also superb and central to our success. And under them, we completed the searches with the first interferometers and saw nothing, just as was predicted. We achieved the sensitivities that we said we would achieve, and we even did a little bit better. And then we installed advanced interferometers, our second generation, and we're ready to begin our search for gravitational waves. But let me say a little bit about the advanced interferometers, describe one piece of noise that we had to deal with in the advanced interferometers. By the time we got to the advanced interferometers, which is what we are currently measuring, we were having to face the fact that each of the mirrors weighing 40 kilograms behaves like a particle, but it's a quantum mechanical particle, just like an electron is. An electron being a quantum mechanical particle, it moves around inside of an atom in a random way. You can't predict where it's going to be inside an atom, just a probability distribution for where it'll be inside the atom. Random quantum fluctuational motions on scales in an atom that are 100,000 times, no, 10 million times bigger than the motions of the mirrors we were trying to measure. And our much heavier mirrors have much smaller quantum fluctuations in where they are, but the quantum fluctuations are at the level of the signals we are trying to measure. Not today, but within about 2 years, we will be at that point. And so we have 40-kilogram particles whose positions are moving around randomly, and we're trying to measure the effect of a gravitational wave on their positions. And obviously, we have a very, very big problem. And it was Vladimir Brzezinski in Moscow who pointed out that we would have this problem already in 1968. And he said we needed to develop then something to deal with this. Because as he said, for the first time in these instruments, humans would see human-sized objects behave quantum mechanically. We had to develop something that Brzezinski called quantum non-demolition technology. What this means is technology to enable us to get a gravitational wave signal through these 40-kilogram particles that are wiggling without this random quantum motion destroying or demolishing the signal. So non-demolition, quantum non-demolition, the quantum motions of the particles don't demolish the gravitational wave signal. And so let me describe briefly how we do this. We had to develop quantum non-demolition technology. And in fact, it was Brzezinski's research group, together, experimental research group, and my theoretical research group that worked hand in hand from 1980 up through the present to develop all the ideas for the quantum non-demolition technology. Carlton Caves, a PhD student of mine, had the key idea for how to deal with this. The key idea is something called vacuum fluctuations. Now, this is a little technical, but I think even non-scientists can understand it if I describe it in this way. Let me take a box, and I remove from the box everything that I can remove. And in particular, I remove all the light that can possibly be removed. we're left behind with fluctuations of the electric and magnetic fields inside here that cannot be removed. They're all the time fluctuating, just like the position of our 40-kilogram particle fluctuates, so the light fluctuates. These are called vacuum fluctuations. And what Carl realized was that if we take our interferometer, our gravitational wave detector, this is the laser beam comes in here, light bounces back and forth, it comes back, it recombines in the photodetector. So this is the output signal here. That's the input of the light. Vacuum fluctuations, these random fluctuations of light, enter the interferometer. You can't stop them. You can't remove them. They're not removable. The laws of physics say you can't remove them. They enter the interferometer, and they beat against the laser light in here, and they cause noise. And in particular, beating against the laser light, they produce fluctuating light pressure on these mirrors. And that fluctuating light pressure manipulates the fluctuations of the mirror positions. And so you have a tool in your hands to manipulate the random motions of this 40-kilogram particle. It's the combination of the vacuum fluctuations and the laser light. So if you can manipulate these fluctuations, thereby you can, through the light pressure, you can manipulate the fluctuations of the mirrors. And Caves realized you could do it by something I'm not going to explain called squeezing. You can manipulate the probabilities for what the fluctuations are doing by doing something called squeezing. And if you do that, you can manipulate the probabilities for the fluctuations in the position of the mirrors. And you can thereby do it in a very, very clever way so that you achieve quantum non-demolition. You circumvent the fluctuations of the motion of the mirror. So anyway, that was the basic idea, and the technology for that has been under development now for about 2 decades, and it is now in hand. It was installed into LIGO a few months ago, just beginning to operate. So I'm going to show you some photos with advanced LIGO interferometers. This is a scene from the air, the Hanford, Washington interferometer. Down inside the corner station here, Barish likes to put a baseball player here to show you the size here. I don't know why he doesn't put a LIGO scientist here, but he put a baseball player here. And this is the vacuum chamber in which that beam splitter that splits the light hangs, and the mirrors, one mirror hangs in here, one mirror hangs in there. The light beams are going out to the ends down there 4 kilometers away. So that gives you some sense. And here is a mirror hanging. It looks like it's being held. It's not. It's just hanging by a fused silica fiber, by a quartz fiber. A single quartz fiber is supporting this mirror, and it's free to move in response to the effects of the gravitational wave. So those are a few photographs. Now, a key issue, before we could go after the gravitational waves, we also needed to understand their sources. And already in 1980, I was pretty sure the strongest sources would be collisions of black holes, and that the strength of the waves would be 10 to the minus 21. It turned out that was the first thing we saw, and the strength of the waves was 10 to the minus 21. So what we were going after already in 1980 was what we actually saw as our first signal. But to learn the waves' details, we had to do computer simulations of the black hole collisions. We couldn't solve Einstein's equations mathematically with formulas, analytically, for colliding black holes. The only way we could solve them to get predictions of the details of the waves was on supercomputers. And the effort to do this had been underway since the late 1950s, beginning in John Wheeler's research group, the group in which I was trained. By the early 2000s, I became alarmed. I had been pushing the people around the world who were doing these simulations that we have to have this when LIGO turns on. If we don't have it, we won't understand the waves that we are seeing. And at that time, my colleagues could not even simulate the orbital motion of a pair of black holes around each other, one trip around each other. Why? Again, let me just give you a brief explanation of one example of the problems. This is for the mathematicians. There's a little bit here for different people who have some kind of technical background. The Einstein equations split into 2 parts, something called constrained equations, which, to use some technical jargon, they are elliptic partial differential equations. And they are the things that you have to solve in order to get the initial data that describe the two black holes as they start to move around each other. And this is a picture of what the two black holes look like as seen from a higher dimension. You're seeing the warped space around the black holes here in terms of funnels that bend down as seen from a higher dimension. I will talk about this in 2 later lectures, tomorrow and on Friday. So anyway, this depicts the warping of space around the two black holes. And then there are evolution equations. These are what we call hyperbolic equations, and they tell you how the black holes move around each other once you have solved these constrained equations to get their initial shapes and properties. Now, we know mathematically that if these constrained equations are solved perfectly, then as we evolve, as we solve these evolution equations, the constrained equations will continue to be satisfied. This is a theorem in the mathematical structure of Einstein's equations. But if the constrained equations are solved with tiny, tiny errors, then as we evolve the two black holes, those errors grow, and typically exponentially, very, very, very fast. And so that was why it turned out nobody could evolve two black holes around each other even once. The computer would crash. But we didn't know that this was the problem. It was in the whole structure of the Einstein equations as we were using them. So we had to reformulate how we were solving the Einstein equations. This was one of many, many difficulties. So doing these simulations from the point of view of the mathematics was in some ways as hard as building the gravitational wave detectors, and it took as long. So having become alarmed, I then, in the early 2000s, I left day-to-day involvement with LIGO to co-found with Cornell, Saul Tukolsky, a former student of mine, who was, I think, the very best of the people working in this numerical relativity, solving Einstein's equations on computers, to co-found something we called the SLS Collaboration, collaboration to simulate extremely curved space-times. And in 2005, one of our postdocs at Caltech in the SLS Collaboration had the first great success with simulating two black holes going all the way around each other, colliding and merging. This was followed soon thereafter by groups led by Joan Centrella and Manuela Campanelli at other locations in the United States. So we had 3 groups that could do these simulations by 6 months after Franz had his first success. And by 2014, the simulations were mature enough for advanced LIGO's first gravitational wave searches. So here we were, September 14th, 2015, the advanced LIGO detectors were being prepared for their first search. The plan was to turn them on in 3 days. And they were sitting there in the middle of the night, turned on, but not quite in their final state. They had to be tuned just perfectly before you started the search. They were sitting there looking at the sky in all directions, and the first gravitational wave signal came in, 3 days prematurely. David Wright, the LIGO director, he declared the first search has begun. We're not going to tune the detectors anymore. We freeze the current state of the detectors. They are tuned as much as we're going to tune them. And we will continue to search for about 4 more months and see what we see. The first signal came in, and this was the first signal. It was so strong you could see it with your eyes. Now, to be slightly technical, this is the stretching and squeezing, stretching up, squeezing down, produced by the gravitational wave in units of 10 to the minus 21. I told you the signal was about 10 to the minus 21. But we have had to remove all the piece of the signal above 300 hertz and below 30 hertz. We call this bandpass filtering for engineers who might be here in the audience. Just remove that because the instruments are too noisy above 300 cycles per second, below 30 cycles per second. And other than that, nothing's been done with the data. And you see the signal here in Hanford, Washington, and you see the signal, in Livingston, Louisiana, you see the signal 7 milliseconds later in Hanford, Washington. and beautiful signals, which when you cleaned them up, they look like these gray traces here. And here's the black holes spiraling together, colliding and merging. And by comparing with the numerical relativity simulations that came from our SLS collaboration, we could infer that the initial black holes weighed 29 times the mass of the Sun and 36 times the mass of the Sun, for a total of 65 solar masses. The final black hole weighed 62 solar masses. 3 solar masses of black hole mass had disappeared, that had gone into gravitational waves. It is as though you had annihilated 3 suns and turned all the mass of those 3 suns purely into gravitational waves. And this happened so quickly, in about 1/10 of a second, that the power output during that collision, the energy per unit time, was 50 times larger than the power that comes off of all of the stars in the universe put together. 50 times the power, the luminosity of the entire universe, coming off of one pair of black holes during the 1/10 of a second that the collision was occurring. This was just absolutely phenomenal. The most powerful event that astronomers had ever seen evidence of, except for the Big Bang birth of the universe. And we could infer that the distance to the source, to these black holes, was 1.3 billion light years. And so you've already seen the movie of what that looks like as seen by your eyes if you were up there close. Here is what it looks like as seen from looking in from a higher dimension. Again, I'll talk about this in my other 2 lectures here in Prague. But we can just watch. So this is the oscillation of the shape of space. The color coding is the rate of flow of time. This has been slowed down into slow motion. This is rather like the ocean in a storm at sea, a huge splash of a wave going up, then paused, then down, oscillating, and that's what produced the gravitational waves. That's what it would have looked like if you were a being that lived in a higher dimension looking in on our universe. We, in our first 2 searches for gravitational waves, saw 10 pairs of black holes collide. That was as of August 2017. And here are simulations of those collisions. And there are big holes, there are little holes, there are all sorts of combinations of black holes, 10 pairs. This is over a period of basically 2 years, 2 gravitational wave searches. Where were these signals on the sky? Well, this is an image of the sky as seen from the outside. And when we had only 2 gravitational wave detectors, we had very poor resolution because the way we determine where the source is on the sky is by the delay in arrival time of the signal at 2 detectors. And the first signal arrived at Hanford, Washington, or in Louisiana, 7 milliseconds before it arrived in Hanford, Washington. Louisiana is south of Washington State. And so the source was in the south. We knew it was in the south. And so the source was at this location on the sky. Antarctica is just below that location. But it was a very long ellipse, and we didn't know where inside this. We needed to have a 3rd detector in order to determine the direction in this other dimension. We got that 3rd detector in August of that should be August of 2017, I apologize. It was the Virgo detector built by a collaboration of France, Italy, Netherlands, Poland, and Hungary. 19 labs, 250 plus scientists and engineers. And with 3 detectors then operating as of August 2017, we had a gravitational wave signal that came in, and we were able to say it was within this little tiny region on the sky. So for the first time, then we had the capability to see where the source was on the sky. Just a few days, I think it was 3 days after this signal came in, 3 days after this signal came in, another signal came in, and it was a signal not from black holes colliding, but from neutron stars. Each neutron star has a diameter of 20 kilometers. It has the mass of 1.5 times the mass of the Sun. It has a density in its core 10 times higher than the density of an atomic nucleus, something like 10 to the 15 grams per cubic centimeter. And as these neutron stars orbited around each other, they emitted gravitational waves, and they spiraled together, and they collided, creating a gigantic fireball of hot nuclear matter exploding outward from that collision and generating every form of electromagnetic waves that is known, as well as neutrinos. The electromagnetic waves were all detected. This is called a kilonova by theorists who had predicted this kind of thing. So we had our gravitational wave signal from 3 detectors. I'm not going to explain this particular way of describing the gravitational wave signal. 1.7 seconds after the black holes collided, as seen by the gravitational waves, there was a strong burst of gamma rays, the highest energy form of electromagnetic waves, that came, and it was in this region on the sky, as seen by the Fermi Gamma Ray Telescope. Our LIGO Virgo gravitational wave detector said it was in that region. And then about an hour later, and then a few hours later, X-rays, ultraviolet radiation, optical radiation, infrared radiation, radio radiation, all of them, the entire spectrum going from the highest energies, photons, the gamma rays, down to the radio waves, all coming in. This was the most studied astronomical event in the history of astronomy. Something like 15 or 20% of the world's astronomers observed it with electromagnetic wave detectors or gravitational wave detectors. We call this multi-messenger astronomy now. The gravitational waves are one form of messenger, X-rays, ultraviolet, and so forth, or other kinds of messengers. And this was the beginning of multi-messenger astronomy. And from the gravitational waves, we knew this was caused by 2 black holes colliding. From the electromagnetic waves, the astronomers were able to verify a prediction that had been made by theorists that there were huge amounts of gold and platinum and other heavy metals created in this collision of the neutron stars. In fact, so much, this is probably where most of the gold and platinum here on Earth was created, in collisions of neutron stars before the Earth was formed, before the solar system was formed. And so these are the kinds of new insights and discoveries that are now coming from this. We began our 3rd gravitational wave search on April 1st. That's a month and a half ago, with improved detectors. If you have an iPhone, I think now perhaps if you have an Android, you can go and get from an app store an app called GW Events, or Gravitational Wave Events. This is a picture of the icon for that app. And yesterday, I went in there and opened up the page there where it lists the events. And these are the discoveries of new bursts of gravitational waves. And so here is a list of the events since April 1st with our improved detectors. We were, during that period, since 2015, we've been improving the detectors. The LIGO team's been improving the detectors. And so down here you see there was a black hole collision that occurred on April 8th. It's a BBH, black hole collision. And it was so strong that such a signal like what was seen would actually be seen within the noise only once in some huge number of years. Once in some huge number of years that's going very far back in geological time. This was definitely 2 black holes colliding. And you can go in and you can click on this and you can see the details of the collision. You can see the details of the searches for neutrinos and electromagnetic waves. Okay, so that was the 8th of April. The 12th of April, another black hole collision. The 21st of April, a very weak collision, 97% probability that it was a black hole, and 3% probability it was just noise. Okay, so we have weak signals as well as strong signals. Keep going. 25th of April, 2 neutron stars colliding. Randomly, this particular signal would be produced by our noise once every 69,000 years. So this is a very believable signal. Then on April 26th, something that is also very weak, that is probably a black hole tearing a neutron star apart, but it might be neutron stars, 2 neutron stars merging. Then on May 3rd, 2 black holes colliding. Then on May 5th, 2 neutron stars colliding. I'm sorry, May 10th, 2 neutron stars colliding. This morning I was taping a TV show here in Prague. And we got talking about, with Daniel, I forget his last name, a very superb interviewer. And we got talking about what LIGO is saying. And so I pulled up my app, and I said, let's just look at it, and I will show you. And I looked, my goodness, this morning there was another gravitational wave collision from two black holes colliding. I made this slide yesterday, and I missed the one that came in this morning. So this shows you what's happening. It has changed from a situation where we might see one black hole collision every month to now seeing, it's been on average about once a week, except, gosh, since the month of May, it's been a half a month, and we have now seen 3 signals in a half a month now. And one on May 10, one on May 15. And you can just get this app and you can follow the discoveries. And you can also follow the electromagnetic discoveries that go along with it day by day by day. A few words then about the future of LIGO, and I will quit. There will be huge improvements in LIGO and also Virgo, other gravitational wave detectors, over the next 2 decades. We will see 10 times farther by the 2030s, or 20 times farther than we do today by the 2030s. We'll see a volume of the universe 20 cubed times bigger, 10,000 times bigger. We'll be seeing every black hole collision that in our mass range for black holes that weigh a few times what the sun weighs, up to a few hundred times what the sun weighs. We'll see all of them back to the earliest moments when black holes formed. That's what I just said. Every black hole collision in the universe with masses less than 200 solar masses, and lots of other things. And there will be, I expect, very big surprises between now and the 2030s. Also, by the 2030s, we will have 3 other types of gravitational wave detectors operating, each measuring different kinds of gravitational waves with different gravity wave periods, sort of the analog of having gamma ray astronomy, X-ray astronomy, optical astronomy, and radio astronomy. We'll have 4 frequency bands or wavelength bands by then. At millisecond periods of oscillation, we have LIGO and its ground-based partners. With periods of gravitational waves of minutes to hours, there will be LISA, the Laser Interferometer Space Antenna, which is a European Space Agency mission with 3 spacecraft that track each other with laser beams, 1, 2, 3 spacecraft tracking each other with laser beams. The wavelength of the waves that LISA sees is 10,000 times longer than the wavelength that LIGO sees. Radio waves that radio astronomers use have 10,000 times longer wavelengths than light does. And so LISA is like radio astronomy if you think of LIGO as being like optical astronomy. And with this, we expect to see black hole collisions where the black holes weigh between 1,000 times as much as the sun and 10 million times as much as the sun. We expect to map the geometry of space, the warped space around black holes with exquisite precision, and we have a good shot at watching the birth of the electromagnetic force, the birth of electricity and magnetism as physical phenomena, the birth of the Maxwell equations that govern electricity and magnetism in the earliest moments of the universe. This is predicted that the force was born in what is called a phase transition, when the universe was 1/1,000,000,000th of a second old. And that phase transition is likely to have produced a random stochastic gravitational waves with a spectrum that we can identify and we can use to watch the birth of the electromagnetic force. I expect that within the next few years we will see gravitational waves using a technique called pulsar timing arrays, which is just with radio telescopes. I will not go into the details. But with this technique, we will see black holes 10 million times the mass of the sun to 10 billion times the mass of the sun, the biggest black holes in the universe. And within the next decade, I think a technique, again, I won't go into details, called CMB polarization. We will see gravitational waves with periods of hundreds of millions of years. Now, of course, that's longer than a student's lifetime. So you don't watch the waves oscillate. Instead, you see a pattern on the sky made by the waves, a so-called polarization pattern of cosmic microwave background radiation. Again, I won't go into the details here. But with that, we will be watching the birth of the universe. we'll be seeing then information coming to us from the earliest moments of the universe, when space and time were being born, then amplified by, with these waves from the Big Bang, amplified by the inflationary expansion, very, very fast expansion of the universe in its earliest moments. So we will be probing the earliest moments of the universe, the birth of the universe, and the phenomena that went on in the first fraction of a second of the life of the universe. That will be the meat, the really exciting things going on with gravitational waves by the middle of this century, and perhaps much sooner. And this will also be seen with a successor mission to LISA called the Big Bang Observer, seen in a very different wavelength band by two different techniques by the 2050s. So let me just conclude by saying that it's 400 years ago that Galileo built his first optical telescope, pointed at the sky, and discovered the 4 biggest moons of Jupiter. And it is now 3.5 years ago that LIGO turned on and saw gravitational waves from the collisions of 2 black holes. When you contemplate the enormous changes in our understanding of the universe that have come in these 400 years since Galileo, using electromagnetic astronomy, I invite you to speculate about what will be done in the next 400 years, what revolutions there will be in our understanding of the universe from combined gravitational and electromagnetic observations. Thank you.
Well, thank you very much, Kip, for this fascinating presentation and for sharing the excitement of all these discoveries. I should start first by thanking to Karel Janeček, who came here, and I notice him already now, who supported significantly the visit of Kip. It was also Learning Society, but
thank you.
I think then I think I shall open the discussion. We will not do very long discussion, but please, questions.
I can answer questions privately afterwards, but we'll do some
That's right. There will be a
discussion
possibility to go there,
I mean,
for those who registered. So.
Let me, before just beginning the discussion, to reemphasize that, well, let me tell you a little story, okay? On October the 3rd of 2017, at 2:15 in the morning, I had a telephone call from the Secretary General of the Swedish Academy of Sciences. He began by saying, it will not surprise you that the Nobel Prize for 2017 will be awarded to you, to Barry Barish, and to Ray Weiss for your contributions to discovery of gravitational waves. I responded, it doesn't surprise me at all, but I'm very disappointed, because the prize should have gone to the team of 1,000 people who made this happen. And it was not me, it was not Barry, it was not Ray. It took 1,000 people to pull this off because it was so complex. And I would have thought that by now, and I think you have an obligation to the world to explain that there are certain pieces of science that are so difficult, it requires collaborations, and superb collaborations to make them happen. And it is really the team that deserves the prize, and the team that should be the public should be made aware of. And I feel that very strongly. And, but the Nobel Prize Committee has not yet learned how to do that. So, go ahead.
Yes, I agree. Actually, Kip included this remark in his Nobel lecture.
Yeah.
I looked at this now. And I mean, Kip is very well known by his modesty. I will just quote you not my letter, which I sent him about 10 days after this, not Nobel Prize, but after discovery. And the answer from Kip came, dear Jiří, thanks you for your very kind words. I am so happy to have been associated with such a superb team of experimenters.
Yeah.
Okay, so let me ask the first question. Yeah. I remember at Caltech was a note by a quotation. There were many quotations and scales of the mass, etc., of the various objects in the universe by Ivor Robinson, And that was that, of course, the correct theory of gravity is general relativity, and if it is not, it at least should be. And of course, it now seems that everything is passing so well, and Kip was always interested in this. He put Cliff Will to do these PPN formalism, etc., which then flourished to compare real relativity with experiment. So what do you think about this possibility of ruling out various theories with these experimenters?
Well, I think the most interesting thing to do is the following, that physicists and mathematicians who work in this area have struggled to understand what Stephen Hawking called the loss of information down black holes. That it appeared that if you formed a black hole through the implosion of a star, say, and then it evaporated through what's called Hawking radiation, that the information that went into the black hole would not come out. And that doesn't bother most people, except the technical phrase of this, it appears that the evolution is non-unitary. That's a physicist's language. And the laws of quantum mechanics, as almost all physicists believe them, unitarity, the non-loss of information, is absolutely sacred. And they struggle to understand this, that black hole physics seems maybe to violate the fundamental tenets of the laws of quantum mechanics. There's been a struggle that has been going on for more than 40 years. And the recent incarnation of this has led some of the world's most respected physicists to speculate that something goes wrong near the horizon of a black hole, and black holes are not the kind of objects we thought they were, that something strange happens just above the surface of the black hole. And so one of the things that we try to do with LIGO, and that will be done with far higher precision with LISA, which will have a much bigger signal strength, signal-to-noise ratio than LIGO, is to search for any sign of something going wrong with the properties of black holes near their surfaces that may be associated with solving this conundrum that physicists that Hawking gave to us, the apparent violation of the fundamental tenets of quantum theory that is tied into black holes.
Yeah, I know you have the bet actually, but let's not speak about bet now, but about further questions if there are. So please. Maybe that you, sorry, could David and...
Don't you have the feeling now that you have too much signal? That because if all this is true, then universe has to be populated by black holes.
Yeah.
In quite unexpected way, I would say.
So
at least for me,
it's still the signal strength is the number of signals is such that there's so many galaxies in the universe that the observational data that we have, I don't know the precise number, but they say that, roughly speaking, that in each galaxy there's a black hole collision once every 100,000 years. And so, but there are so many galaxies that what we are actually seeing now is something like 1 a week or 2 a week. And we expect when we reach our design sensitivity for the initial detectors, which will be about 2021, it will be 1 a day. And we expect that it is going to be something more like 1 every few minutes by the time we reach the 2030s. But still, that's just 1 every 100,000 years in the Milky Way galaxy. It's just the universe is so big and there's so many galaxies.
Yes, please.
I was wondering, when you were describing this multi-messenger event, it was surprising to me that the different waves of light were arriving at different times. Could you explain for a non-expert why is it so? Because it's the same moment in time when it happens there. Right?
So the issue is that the material from these neutron stars was very, very dense. And so the electromagnetic waves could not get out because it was trapped inside this very hot material. The surface was so small that it wasn't emitting strong enough off the surface for us to see at this great distance. You had to be able to see down into the interior. And so this fireball, as I called it, of very hot matter expanding very fast, it became less and less dense. And the first thing that could penetrate from the interior, the first thing was gamma rays. And then when it became less dense, and that's 1.7 seconds after the collision. And then about an hour after the collision, the X-rays could get out. And then a few hours, the light, the ultraviolet, then the light, then the infrared, ultimately a few days, the radio waves. So it was just because the matter was so dense that these longer wavelength forms of radiation couldn't get out until it had expanded farther.
So there's just one speed of light.
So there's just one speed of light, and one speed of gravitational waves. The fact that the gamma ray burst came within 1.7 seconds of the black hole, of the neutron star collision, tells us that the gamma rays and the gravitational waves traveled at the same speed to within an accuracy of 1.7 seconds divided by, I have to now do a conversion, it's about 60 times 380, by about 200 million years, because the distance that was traveled was 200 million light years. So 1.7 seconds, 200 million years is 2 times 10 to the 7 times 3 10 to the, 2 times 14. So that's about 1 part in 100 trillion is the accuracy with which the light, the gamma rays, and the radio and the gravitational wave propagated at the same speed. From this one observation, experimental data, gravitational waves and gamma rays travel at the same speed to about 1 part in 100 trillion, 1 part in 100 trillion. I may have not done the numbers quite right in my head. That's close to what the number is.
So they are called firewalls like with black holes, are they? Because this is what you mentioned about the information paradox. They speak about firewalls above horizons, but those with neutron stars, the matter is called in the same way.
No,
sorry. I saw that firewalls is usually confined to this problem of information paradox and horizon. But
so in colloquial American language, a fireball is anything really hot that's expanding fast.
Okay.
So
fine.
Yeah.
Okay, sorry. So
we use these ways in different.
Yeah. So here was the question.
Is there a theoretical limit on the frequency of these?
No more so than there is on the frequency of electromagnetic waves. But there is an astrophysical limit in this sense that to produce strong enough gravitational waves for us to detect them, we need objects that are very massive and very dense, that have very strong internal gravity. And in our astrophysical universe, it turns out that these objects, the only ones that exist are neutron stars and black holes that are really that dense and that heavy. And the frequency of the waves from these is basically the frequency with which they go around each other and collide. And those frequencies get up to about 10,000 hertz, but not higher. So one circuit around each other, because these are big objects. So one circuit around each other in 10,000.
So that's the bandwidth at which you have to observe.
So we actually can only go up to about 1,000 hertz. So we work in the band between 10 hertz and 1,000 hertz. We're not yet able to, with decent sensitivity, go up to 10,000 hertz. So our frequency band of operation is between 1 hertz and 10,000 hertz. And the data are collected, however, with basically at a frequency of 10. Our observational band is 10 to 1,000 hertz, but the bandwidth of the data is actually 10,000 hertz. So we collect the data, a data point basically once every 10 to the minus 4 seconds. So the bandwidth of our data is 10,000 hertz, but we have decent sensitivity between 10 hertz and 1,000 hertz, 1 kilohertz.
Okay.
Hey, you were saying that you have some new methods how to remove the quantum fluctuation from the data, right? Can you somehow give me a hint to elaborate on that, how that could be done?
Okay, so dealing with the quantum fluctuations of the, as I argued, dealing with the quantum fluctuations of the mirrors, which we think of as then 10 kilogram particles, goes hand in hand with dealing with the quantum fluctuations of the light. Because we use the light pressure from the beating of the vacuum fluctuations of the light against the laser light to manipulate the quantum fluctuations of the particles. So the key to then dealing with both the quantum fluctuations of the light and of the particles is manipulating the probability distribution for the light's quantum fluctuation. This is done by a technique called squeezing, where you decrease the magnitude of the fluctuations at 1 quadrature of oscillation. Say, pick a frequency, and the cosine omega t quadrature, you squeeze the noise, you decrease it at the price of increasing it in the sine omega t quadrature. But then you have to do that at each frequency and with a frequency-dependent squeezing. And so it's a complicated story, but the key thing is the technology of squeezing, and this is achieved by taking a crystal called a nonlinear crystal, and you send laser light that you're using into the crystal to pump it, and then you send the vacuum through the crystal. It interacts nonlinearly with the pumping due to the laser light, and it can be, thereby the laser light, the vacuum fluctuations get squeezed. So it's a technology that has taken 2 decades to develop and to bring into our frequency band, but it is an amazing technology, this business of squeezing, which is now being used rather widely in other areas of high technology. But it was what we needed, it turned out, also for our gravitational wave application. So this is a kind of a complicated subject, but it is a beautiful, beautiful technology.
Okay, well, I will first ask here Elisabetta, because she asks questions every lecture I give, so she should give the question now, and then you will.
Thank you very much. My question is connected to the simulation of the merger in black holes. I am confused about the moments right before the merging. It seems that some effectively anti-gravitational effect is there because of the hills on the simulation when we see the merging. So what kind of the interaction causes that?
So I didn't understand why you say there's an anti-gravitational effect.
Well, I mean that when we see the black holes, it is the holes on the simulation, and then right before the merging, there is some hills. So the
these hills that.
Yes,
yeah.
I mean that.
Okay, so what you're seeing, so gravity, as we're accustomed to it, that holds us to the surface of Earth, is in some deep sense caused by the warping of time, not by the warping of space. And I can describe it this way, that was something that, in fact, that Einstein first understood, I think, began to understand when he was here in Prague in 1911. He developed a theory of gravity that was based on the warping of time. In this theory, this also became incorporated into part of general relativity. And I describe it in this way: Einstein's law of time warps is my phrase for it. That things like to live where they will age the most slowly. Now, I would like to live where I will age the most slowly. And gravity pulls them there. And so there's a precise mathematical formulation of this. And the key thing then is that time flows more slowly on the surface of the Earth than at high altitude. And it is this difference in time flow that causes the gravity that holds us to the surface of the Earth. There's a precise mathematical description of this that the fractional slowing of time, you take the gradient of that in the mathematical terms, and that gives you the gravitational acceleration that we feel. And so, and that at least when the gravitational field is not changing rapidly, that's incorporated in general relativity. And so the warping of time is the key to the gravity that we feel. But what I was showing you was the warping of space around the black hole. And the warping of space had this strange effect that around the black hole, space is warped like a funnel, and you have two funnels going down, or like the surface of the water in a whirlpool around an exit in a bathtub, for example. So you have the black hole as seen from a higher dimension, looks like two funnels that are going around each other, these binary black hole. But when they collide, space, not time, and not the gravity we feel, space creates these two huge splashes on the sides. Why? I don't really understand. That's what the computer says. And you're now in a regime where the physics that's going on is so nonlinear, for those who understand that phrase, that we don't know how analytically to explain this yet. I think we may in due course, but that's what the computer says. It says creates these two splashes on the sides opposite to where the collision is occurring. And those play a big role in producing this enormous amount of gravitational waves that is coming off, this enormous power.
You mentioned that we will be able to localize the sources of gravitational waves in about 2050. Well, but you also show us this map where we could see that we already now localize them with the accuracy, say, 10 degrees squared. So you meant localize them with such precision as we localize optical sources? And if so, how it can be done? Wouldn't we need something like LISA, but with 3 LIGOs in the vertices of the triangle?
So what we expect, I don't think we will we probably will not during the 21st century do it as well as light is done, but we'll do a lot better than we are now doing. Much, much, much better. And the key to this is you take LISA in space, this triangle of spacecraft, and you put 3 LISAs at 3 different locations around the Earth's orbit. And so it's like taking, in radio astronomy, taking a radio telescope and putting it in North America and another one in Europe and another one in South America. And then you combine the data from these 3 radio telescopes and you get marvelous angular resolution, similar to what you would get if your radio telescope was as big as the Earth. Well, here the plan is to have 3 LISAs. Well, actually 6. You have 2 LISAs that coincide at one location, and then 1 here and 1 there. This is for complicated reasons of getting rid of foreground noise from other sources. That you need basically 6. You need 4 of these things: 2 here, 1 there, and 1 there. And so you get a gravitational wave detector that is of a total size. It's about the size of the orbit of the Earth around the Sun. And now you have a detector that is much, much bigger than the wavelength of the gravitational waves that you're going after. You're going after gravitational waves that have wavelengths somewhat like the separation between the Earth and the Moon. And, but the detector now is as big as the orbit of the Earth around the Sun. So you then get far, far, far better angular resolution than we can now get. And that will be the instrument which will also then, because of this angular resolution, that's part of it, it will be able to remove the signals that are coming from black holes colliding and everything else in the frequency band of this giant detector, and have only left the gravitational waves from the Big Bang. And so the goal then, you'll have huge, wonderful, accurate angular resolution on things like colliding black holes. You see them, remove them from the data, and what's left is the stuff that came off the Big Bang. That's what is going to be really exciting. And so I was born in 1940. My goal now is to live till 2050 and maybe see this happen. 110, I think, is a reasonable goal.
Well, you suppress now the fact that you are coming from the family which is long-lived.
Yes, that helps.
So you have good genetical prepositions.
Yeah.
Before I allow the last question, I think I should say, because you can come to us, to the faculty, which will be completely open, not registered, or on Friday, and then we, well, they have theater, black theater in the evening, but still, we can do longer discussions there. We should shift there. But before I ask Michal Křížek to ask last question, so let me say that, sorry, today, around 2 o'clock, Gabriela Cihlářová, who is real source of inspiration for Daniel Stach for these Hyde Park civilizations, phoned me and said this was one of the best interviews they ever made with Kip. However, they have holidays now. It seems that this Hyde Park civilization stops in May or whatever. And so most likely this Hyde Park will be in September. So just watch or have a look. Okay, so Michal, the last question.
Gravitational redshift of any black hole is infinity. Yes? So if you send any object there, it takes theoretically infinite time. So how can you explain that the collision of two black holes takes, say, several milliseconds only? Yes.
Because the gravitational waves that we see are produced by the curved space-time, the warped space-time outside the horizon, in the region basically between close to the horizon and a region say something like 2 or 3 times the size of the black hole away. That's where most of this warping of space and time occurs. And so all of the things that we're dealing with are the phenomena of what the black holes are doing in that region. And the slowing of time is quite modest in that region. We're not going... Now, I mentioned that we would really like to explore possible failures of general relativity near the horizon. And so there's going to be a question of how close to the horizon can we get with our data in order to search for these things that are speculated to perhaps occur. And so this then will start to become an issue. But for the things that we're doing currently, we're bounded away from the horizon by the region in which the waves are actually produced is a larger region.
Okay, I think we should stop. This is a very well-known astronomer, but you can ask Kip then if you are registered for banquet. Let's stop now.